You know the feeling. You're squeezing the cold metal handle at the gas station, listening to the rush of liquid, when suddenly, snap, the handle jolts out your grip with a loud click, and the flow stops entirely on its own. Gasoline is highly flammable, and a spill is a major hazard. The pump has to stop at the exact millisecond every single time to keep you safe. But if you look closely at the nozzle in your hand, you'll notice something strange. There are no optical sensors to look into your tank. There are no batteries and no microchips processing data. So how does a completely dumb piece of metal know exactly when to stop pouring gas? The nozzle functions as a hidden mechanical computer, solving a dangerous problem through a series of physical reactions designed decades ago. To trace how this works, we have to follow the fuel. An electric motor pulls gasoline up from giant underground storage tanks, forces it through a positive displacement meter that counts your gallons, and pushes it up into the flexible hose. But the control happens when we look inside the nozzle itself. It's a tightly packed machine with three critical components. First is the main valve. Think of this as a heavy steel door that blocks the flow. It only opens when you physically squeeze the handle to let the gas through. Second, hidden up inside the handle, is the diaphragm. It is a thin, flexible sheet of material that acts like a tiny rubber trampoline. Third is the sensing hole. If you check the very tip of the metal spout, you'll find a pin-sized opening. This hole is connected to a small, hidden air tube that runs all the way back up the spout, ending in a sealed chamber right behind that rubber diaphragm. Together, these three mechanical pieces are perfectly positioned to turn the flow of liquid into a precise physical movement. The engine driving all of this is a principle of fluid dynamics called the Venturi Effect. When a fluid is forced through a narrow pinch in a pipe, it speeds up. As it speeds up, the fluid's pressure drops, creating a localized vacuum or suction force right at the bottleneck. You can see this invisible force at work in everyday objects. It's exactly how a vintage perfume sprayer pulls liquid up from the bottom of a bottle when you squeeze the bulb. Inside the gas pump, as gasoline flows through a narrow section of the nozzle, it generates that exact same vacuum. This vacuum constantly sucks air in through that tiny sensing hole at the tip of the spout, keeping the internal pressure balanced. As the gas level in your car's tank rises, it eventually reaches the tip of the nozzle and completely covers that sensing hole. Suddenly, the air is blocked. The vacuum tries to suck up gasoline instead, which is much denser. This abruptly redirects the suction force, violently pulling on the flexible rubber diaphragm. The jumping diaphragm trips a metal latch. That latch releases a spring, which slams the main valve shut in a fraction of a second. Click. The gasoline itself acts as the trigger, using its own fluid dynamics to cut off its own flow exactly when the tank is full. Of course, you've probably experienced the pump clicking off early, cutting your flow when the tank is barely half full. This happens because you're pumping too fast. Gas splashes up, or hot summer vapors rise out of the tank and temporarily block the sensing hole. These nuisance clicks demonstrate the extreme sensitivity of the mechanism, which is designed to react to any obstruction in less than a second. Modern nozzles adapted to stricter environmental laws, adding bulky rubber boots to recover harmful, smog-creating vapors. Beneath external upgrades, the core shutoff mechanism is so perfectly calibrated it hasn't needed an upgrade. This automatic shutoff was actually invented all the way back in 1939 by Richard C. Corson. While today's gas stations are packed with complex electronics, those modern microchips only calculate your pricing and track the volume. They have zero control over stopping the liquid. The physics of the Venturi effect driving that click is incredibly robust. It is the exact same physical principle used to mix air and fuel inside the massive carburetors of vintage airplanes. Brilliant engineering doesn't require electricity. Sometimes the most reliable way to solve a problem is simply to harness the invisible laws of physics. What other seemingly dumb everyday objects do you think might be hiding secret physics magic inside them? Let us know in the comments below.